Okay, so this is the moment you've been waiting for ever since week 1. How to actually prove programs correct. So let's go back to that example with which we launched week 1 and week 2. Here's the code. What is it supposed to do? It's supposed to sum the elements in array B where the size of array B is n. And what does it do? It initializes a variable s in which you're going to accumulate the sum to 0, and then you initialize the loop variable k equal to 0, and then you count a loop. You add elements of b to s and you increment the loop index. So in week 1 you were introduced to the principle of mathematical induction, and you may have noticed in the launch for week 2 that the explanation that motivated that the code may be correct really looked an awful lot like mathematical induction. And indeed we claimed that it was mathematical induction at work. Now how can we convince you of that? Well, here we have annotated once again that same code segment, and notice that we have used English sentences to make things a little clearer. And what we reason here is that before the while loop starts, S contains the sum of the first k elements of B. Now why is that true? That's true because S is set to 0, the k is equal to 0, and if you sum over the empty range, then indeed you get 0. So that's like the base case for mathematical induction for the case where k is equal to 0. And then what we reasoned was that if at the top of the loop S contained the sum of the first k elements of B, then the update in the loop put us back into a situation where S equaled the sum of the first k elements of B. And notice that along the way k was incremented by 1. Now that's very much like an inductive hypothesis. S equals the sum of the first k elements of B. And then the inductive step, where you show that if it's true for k, then it's also true for k plus 1. So what can we conclude from that? We can conclude from that every time through the loop, S equals the sum of the first k elements of B at the top and at the bottom of this loop. Now notice that if we ever get into the situation where the loop guard becomes false, then we come out of the loop. But no computation happened between the assertion at the bottom of the loop, S equals the sum of the first k elements of B, and the check that we did to see whether we should stay in the loop, k less than n. So that means that when we come out of the loop, it's again the case that S equals the sum of the first k elements of B, but now it's no longer the case that k is less than n. And since k is no longer less than n, we conclude that the k is equal to n, and therefore we have computed the sum of the first n elements of B. In other words, we have computed the sum of all elements of B. So that's mathematical induction. Here we say exactly the same thing, except that we use mathematics to say it. Now, this condition that holds before and after each iteration of the loop, and therefore holds before the loop starts and when we come out of the loop, is called the loop invariant, and it is key to proving that a loop executes correctly. Here we've taken away the specifics of this example. So what do we have here? We have the precondition Q and the postcondition R. We would like to show that this loop takes us from a state in which Q holds to a state where R holds. We have this predicate called the loop invariant, which we would like to be true at various points in this while loop. If we can show that Q implies the loop invariant, then we know that the loop invariant is true before the loop commences. That is like the base case in mathematical induction. If we can show that if the loop invariant holds as well as the loop guard before S, then we will again end up in a state where the loop invariant holds. Then we can conclude that the loop invariant holds before and after the statement S every time through the loop. That's the inductive step in mathematical induction. Eventually, hopefully, the loop guard becomes false, at which point we come out of the loop, but notice that we knew that at the bottom of the loop, after statement S, the loop invariant was true, and therefore we can conclude that the loop invariant is true after the loop, but now also the loop guard is false. If we can then show that the fact that the loop invariant holds and the loop guard is false implies R, then we know that this code segment is correct. What we haven't discussed is how to prove that eventually the loop guard becomes false. That's important because otherwise you may end up in an infinite loop, and notice that we want commands to finish. Otherwise you can't say that they finish in a state where the post condition holds. What we're going to do for the remainder of this section is work out the details so that you learn how to prove a loop correct.